Alright, it's time for LeetCode Weekly Contest 190. In this video, I'll be doing the contest, and then afterwards, I'll be going over the problems and explaining my solutions. Alright, it's time to go over Weekly Contest 190. Personally, I found this contest not as difficult as the other ones because I solved all the problems within 36 minutes. So let's go over the solutions to the problems now. Problem 1. Check if a word occurs as a prefix of any word in a sentence. You're given a sentence that consists of some words separated by a single space and a search word. You have to check if search word is a prefix of any word in sentence. Return the index of the word in sentence where search word is a prefix of this word, and you have to return the minimum such index. If there is no such index, then return -1. This is a pretty simple problem. We split the sentence up into words and make an array, and then we loop through the array, check if the prefix is a prefix of any word, and if so, we return that index. Otherwise, we return -1. Problem 2. Maximum number of vowels in a substring of given length. You're given a string s and an integer k. Return the maximum number of vowel letters in any substring of s with length k. This is a pretty classic window sliding problem, or sliding window problem. Basically, we have a window of length k, and then we always keep track of how many vowels are within that window, and then we move the window along so we don't have to reevaluate the substring of length k every single time. Basically, what this means is we start with the first k letters, we count how many vowels are in that, and then we do some iterations. Each iteration, we shift the window to the right by 1. If the letter that was previously at the end is a vowel, then we can subtract 1 from the total count, and if the letter that we just added is a vowel, then we can add 1 to the count. And essentially, this means we can have the count of every single substring of length k throughout the string in linear time. And that means at the very end, we can just return the maximum. Problem 3. Pseudo-palindromic paths in a binary tree. You're given a binary tree where node values are digits from 1 to 9. A path in the binary tree is said to be pseudo-palindromic if at least one permutation of the node values in the path is a palindrome. Return the number of pseudo-palindromic paths going from the root node to leaf nodes. This is a DFS problem. Basically, for each leaf, we look at the path that goes back to the root. And this path, we have to evaluate how many times each digit shows up. Using this, we can see if the path is pseudo-palindromic. We can determine that by looking at the total number of occurrences for each digit. In a palindrome, the key feature is that the left and right parts are the same, which means that the number of occurrences each digit has must be even because it's replicated on both the left and the right sides. Of course, if the length of the palindrome is odd, that means the middle digit does not get replicated, and that means we'll have to do an edge case for that. But basically, that's how we tell if a path is pseudo-palindromic. We look at the counts and we see if it's even. Then we do the DFS, and once we get to a leaf node, we look at the entire path, see if it's a palindrome. If so, we add 1 to the total, and yeah, that's it. Problem 4. Maximum dot product of two subsequences. You're given two arrays, nums1 and nums2. Return the maximum dot product between non-empty subsequences of nums1 and nums2 with the same length. A subsequence of an array is a new array which is formed by deleting some of the elements of the original array while preserving their order. So, first, let's explain what a dot product is. If we have two example vectors or arrays of length 4, the first one being 4, negative 3, 1, 0, and the second being 2, 7, negative 6, 2, we can compute the dot product by going through the indices and multiplying. So suppose these are the two arrays, and we multiply the elements at index 0. We get 8. 4 times 2 is 8. Index 1 is negative 3 and 7. That's negative 21. And we keep going. And at the end, we add up these products. So, for example, this would be negative 19. That's the dot product of these two arrays, and it's an integer, not another array. Basically, how we do this is we create a DP table. Let's write this out. The element at dp ij is equal to the maximum dot product subarray. So basically, this means we're doing a smaller version of the original problem of the first, if the arrays are A and B, so let's say the arrays are A and B, the first being A1, well, okay. So the first one going up to I, and the second one going up to, oops, we should have a 0 here. And the second going up to J. And we're not including I and J here. Basically, what this means is we can do the transition pretty easily. So, for example, to calculate dpij, we can do dp I minus minus 1j, because that's essentially just restricting us even further, and that means if we expand the restriction, that means we can still do it. And so these two values have to be considered because they can be constructed while computing dpij. Additionally, if we only look at the two arrays that do not include I and j, so if we do A012 ... I minus 1 and B012 J minus 1, that means we're not including I and j, I minus 1 and j minus 1. So if we have these two subarrays that we're calculating the maximum dot product subarray on, that means we are leaving I minus 1 and j minus 1 up for multiplication. So if we're only if we're going to use these two arrays, that their maximum dot product subarray is going to be dp I minus 1 j minus 1. And then additionally, since we have I minus 1, oh no, this is okay, how about this? We're leaving I and j up for multiplication if we're not including I and j. So the maximum dot product subarray of these two arrays is going to be dp I minus 1 j minus 1. And then additionally, we can add on I times j. And if this doesn't help, then the value of dp I minus 1 j minus 1 is already included here. And if we add it on, that's great. So we will take the maximum of that. So we will take the max of I minus 1 j, I j minus 1, and this. Essentially, what we're doing here is we're looking at existing solutions. We're taking the max of those to see if they work, if they're helpful. Otherwise, we can take the product of AI, BI, and look at what is left and take the maximum of that. That's the DP step. So once we take the maximum of that, we can calculate the value of dpij. But there's one caveat. What if the optimal solution is just to create arrays of length 0 so that the dot product is 0? Well, we know that they have to be non-empty, right? So if the optimal solution is just to have empty arrays, that means every single product has to be negative. Every single possible dot product has to be negative. Otherwise, we could just return positive instead of 0. So what this means is we want to calculate the least negative such dot product. And to do that, we will look at, we will only consider taking arrays of length 1, because otherwise we'd have even more negative numbers, right? So to do that, we do an n-squared algorithm where we loop through every combination of pairs of subarrays of length 1, and then we take the maximum of that to have the least negative. And at the end, if our answer is computed to be 0, which means that it's optimal to actually have no subarrays, but we can't do that, so we returned our computation. Yeah. So overall, I think this was a pretty easy contest for me. I kind of zipped through the problems. Problem 4 is kind of difficult to explain, but it wasn't a hard problem. It's not hard by problem 4 standards. It's just like a standard problem, like a standard dynamic programming problem. So yeah, this was a pretty easy contest for me. Great, so thanks for watching the video. I hope you enjoyed it. Goodbye.